We're going to do some more problems involving inverse trig functions. And now here's where it gets a little interesting. Let me just give you some examples of some problems that we're going to solve, and then we'll talk about how to determine what they are. Sometimes you have things like this: the sine of the inverse sine of 1/2 equals what? You might have the cosine of the inverse cosine square root of 3/2 equals what? But then sometimes they flip it around, and you can take the inverse cosine of the cosine of 2 pi over 3. Or you can have the inverse sine of the sine of 5 pi over 4. Now some of you, if you recall back when we first started learning about inverse trig functions, we said one of the purposes of an inverse trig function, if we think down to these two examples, we talked about an inverse trig function will cancel out the trig function, and you're just left with what's inside. When you first started talking about inverse trig functions, that was the whole reason, because this gives us a way to sort of cancel out or reverse the same trig function. So you would think inverse cosine cancels the cosine 2 pi over 3. You would think inverse sine cancels out the sine. You're just left with what's inside, 5 pi over 4 up here. Even though they're reversed, it sort of makes sense that the cosine and the inverse cosine would cancel out, and therefore this answer is square root of 3/2. And the same thing up here. So this would be sort of common sense from our understanding of inverse trig functions. But what I'm going to do is, for now I'm just going to mark those out, because some of those I believe are not actually correct, even though actually it would be nice if they were all correct, because life would be simpler, but they're not all correct. Some of them are, some of them aren't, and now we have to go through some rules to sort of decide what's what. And these actually are given a name, and I'll use this name. These are called cancellation rules. It's almost like they're aware that when you have inverse trig functions and trig functions, that the tendency is they should cancel out. The problem is they don't always cancel out. There are certain times they do, and now what we're going to do here, we're going to list the rules for when they actually cancel out. So there are times when life is good and the trig functions do cancel out. But sometimes you'll have a problem where they actually don't cancel out. So the key for us is to understand when do the trig and inverse trig functions cancel and when do they not. So let me just write down, let's do the rules for the sine first, and then do some examples. So let's do where we take the inverse sine function first. So we put an x in here. This x is actually an angle, right? So now we want to know When is this true? When can I take the inverse sine of the sine of an angle and it just equals the angle? When do these things actually really cancel out? And you're just left with what's inside. That can happen, but here's the restriction. It only works if your starting angle is between negative pi over 2 and pi over 2. If this looks familiar, this is the same limitation that we had on the inverse sine function. Remember we said whenever you take an inverse sine function, the answer or the angle always has to be between negative pi over 2 and pi over 2. The same thing here. So for instance, if we were given this problem, the inverse sine of the sine of pi over 4. First thing you do is you say, okay, does this angle in here, does this fall within my cancellation rule where I can cancel out? Cancellation rule says, hey, as long as your angle is between negative pi over 2 and pi over 2, cancellation rule works. In this case it is. So right away, I don't really have to do any trig or any math. I just edge pi over 4. All right, let's do another one. Let's say we're trying to figure out the inverse sine function of the sine of 3 pi over 4. I would like to use a cancellation rule. That would make the problem very easy. Let's see if it applies. I go up here, and I look and I say, well, is my angle between negative pi over 2 and pi over 2? Turns out it is not. Can't use now you don't just stop. It's not like there's no solution. We can actually work out this problem, but we just have to work it out sort of one step at a time. And what you normally do is you work from the inside out. In other words, I'm going to take the sine of 3 pi over 4, and I'm going to ask, what is the sine of 3 pi over 4? Well, once again, unit circle. If you go find 3 pi over 4, it's right here. What's the sine? The sine of that angle is square root of 2 over 2. So this thing is square root of 2 over 2. So this becomes the inverse sine the square root of 2 over 2. So now I ask myself, what is the inverse sine of square root of 2 over 2? Now, since this is an inverse sine, I have the restriction, right? I'm looking for an angle somewhere between negative pi over 2 and pi over 2, where the sine is square root of 2 over 2. Well, I know it's this angle right here, which is actually pi over 4. So it turns out this is pi over 4. So if I go way back up here to my original problem, it's true, I cannot use the cancellation rule. I can actually put an answer down, but it's pi over 4. You notice they're not the same. So when we take the inverse sine of the sine, we hope we can use our cancellation rule, but we have to check. And if the angle is from negative pi over 2 to pi over 2, we can use it. Beautiful. If our angle is outside this range, then we just have to do it the old-fashioned way. Now let's think about cosine. When can we use some cancellation rules for cosine? So when does the inverse cosine and the cosine, when do they cancel out? Well, if you think about what happened with the inverse sine, where the restriction was the angle has to be between negative pi over 2 and pi over 2, well, common sense might say, since we're not talking about inverse cosine and cosine, this cancellation rule works, but you know what now? The initial angle has to be between 0 and pi, which makes sense because this was like the same restriction when we're trying to do an inverse cosine function. So once again, I have the inverse cosine of the cosine of pi over 6. I'm going to cross my fingers and hope the cancellation rule can be used. So I go check my angle. Is pi over 6 between 0 and pi? Yes, it is. So therefore, I can just right away say that is pi over 6. What if I say the inverse cosine of the cosine of 5 pi over 4? Once again, cancellation rules make life easy. Can I use it here? If I go check, 5 pi over 4 is not within 0 to pi. So I cannot use the cancellation rule. Instead, I just have to do it sort of a step at a time the long way. Let's go here first and let's say, okay, so what's the cosine of 5 pi over 4? 5 pi over 4 is right there. We know the cosine is going to be negative square root of 2 over 2. Now we ask ourselves, okay, what's the inverse cosine of negative square root of 2 over 2? Now we have to keep in mind, since we're doing an inverse cosine function of our restriction, this angle is going to have to be between 0 and pi. So I go up here, if I'm looking just in the top half, for what angle is the cosine going to be negative square root of 2 over 2? Right here. And that angle is 3 pi over 4. So once again, the initial problem, inverse cosine of the cosine of 5 pi over 4, does not equal 5 pi over 4. Instead, it equals 3 pi over 4. So just to keep this straight, when you take the inverse sine of the sine, the cancellation rule works. If the angles between negative pi over 2 and pi over 2, if we take the inverse cosine of the cosine, the rule works if we're between 0 and pi. Now, just to make it more interesting, we can switch these. In other words, for both these two we've just done, we actually looked at taking the inverse sine and the inverse cosine first. How about what would happen in the cases where we take the sine of the inverse sine function? Once again, I would like for those things to cancel out. When does that occur? Now you notice inside here, this x here, we're taking the inverse sine function. This whole thing inside the parentheses is going to end up being an angle. So this right here is the number. And let me just write out the rule. And then we'll do some examples and you'll see it. The cancellation rule for this works if the x in here starts out between -1 and 1. So for instance, can we use the cancellation rule? You go in here, you look, you have 1/2, and you say we can use cancellation rule if the x is between -1 and 1. It is now I'm going to do this problem according to the rule, but then I want to talk about it because it's sort of, you can see why this makes sense. So now I say, okay, here's the second problem. Can I use the cancellation rule? Well, the sine and the inverse sine cancel out. Here's my number 2. Is it between -1 and 1? It is not. So unlike the other problems, at this point, well, we can, okay, let me not do that. Let's just say, okay, well, let's just try and sort of do this the long way. So this right here is going to be an angle. So I got to figure out, okay, let's go find an angle where the sine of that angle is 2. And you know what? It doesn't exist. The sine of an angle is never 2. The sine of any angle always has to be between -1 and 1. So this is actually undefined. So this whole thing is undefined. So just to sort of, I know it's starting to pile up, starting to get a little deep, but just to think, when we do the inverse sine first, it's like you're always going to get an answer, even if your initial angle is outside the limit for the rule, you still can work it out. But what's interesting is when we do the sine of the inverse sine, okay, if we can use the rule, it's great. But you know what? If we can't use the rule, there's actually nothing we can do. It's actually undefined. And the cosine's the same way. When can I use the cancellation rule? If my starting number here is between -1 and 1, so if I say what's the cosine of the inverse cosine of 0.2, you say, well, I hope I can use the cancellation rule. Let's see if my number's okay. My number's 0.2. Cancellation rule says it has to be between -1 and 1, which it is. So I can right away say 0.2. Another problem. Cosine, the inverse cosine of -5. You're like, okay, I hope I use the cancellation rule. Can I? Well, -5 is not between -1 and 1. Undefined. All right, now the last thing that we do with inverse trig functions, as if we haven't done enough already, here's the last thing they're going to do. They're going to sort of mix and match some of these inverse trig functions. What do I mean by that? By that I mean, let me get my example. How about they say please determine the cosine of the inverse sine of 1/2. So you notice now it's like we're mixing and matching. We've got a cosine trig function and an inverse sine trig function. You have problems like this, there's no shortcuts, no rules to make it easy. You just have to work from the inside out. Here's what's going to happen. Sometimes, like this one, so this is going to be, since it's an inverse sine function, I keep telling myself this thing is going to end up being an angle. So I'm going to, in a minute, I'm going to find out what this angle is, and then I can take the cosine of that angle. Now in this case, in my head, I can determine this angle, because actually this is going to be one of my special trig angles. In a minute, we're going to do a problem where it's not a special angle, and then you're going to have to do some extra work to solve this problem. But for now, I say to myself, okay, let's go find an angle. And remember, I've got this restriction, has to be between negative pi over 2 and pi over 2. Let me go find an angle in there somewhere where the sine is 1/2. It's right here, right? Pi over 6. So basically, this then becomes a problem of cosine of pi over 6. And what is the cosine of pi over 6? Square root of 3 over 2. So this whole thing equals square root of 3 over 2. What about let's take the inverse sine of the cosine of 7 pi over 4. So once again, since I'm sort of mixing and matching, there's no special rules. You just have to work from the inside out. So first I say, well, what's the cosine of 7 pi over 4? It's in the fourth quadrant, right? Right here. I think it's square root of 2 over 2. So this becomes inverse sine, square root of 2 over 2. And now, this whole thing is an angle. Got to go find the angle. So it's an inverse sine. It's got to be between negative pi over 2 and pi over 2. And square root of 2 over 2 actually is right here, which is pi over 4. So this whole thing equals pi over 4. Okay, now those are examples where the numbers all allowed for me to use special angles. But now sometimes they're not going to, everything's not going to be a special angle. How about a problem like this? The cosine of the inverse sine of 2/3. So the first thing I say to myself is, since I've got an inverse trig function, if I can figure it out, this is going to be an angle. Now, in this problem, they're going to ask for an exact answer, which means you can't go grab your calculator, because your calculators do have inverse trig functions on them, but that's not going to be allowed. We need to have an exact answer. So I'm really looking for what is the angle where the sine is 2/3. That is not one of my special angles. I don't, off the top of my head, know that. So basically what I have to do is I am going to go and take this, I haven't really done this yet, but let me write this out. Inverse sine of 2/3 equals theta. You know what I can do just for fun? How about I take the sine of both sides of that. Now if I look here and you go back to your cancellation rules, this number is between -1 and 1. So this side equals 2/3. So in a sense, the theta I'm trying to solve for up here, I can think of it as the sine of theta equals 2/3. And you know what I'm going to do with that? I'm going to create a right triangle where theta is here. If the sine of theta is 2/3, sine is so opposite over hypotenuse, which means this side here is going to be 3 squared minus 4 squared, minus 2 squared. Because that's 9 minus 4. This bottom side is square root of 5. So if I call this inverse sine function theta, in a sense, I can rewrite this as cosine theta, and this cosine theta is actually this theta here. So now I say, well, I've created this triangle based upon the inverse sine. So if I say, what's the cosine theta? It's so ca adjacent over hypotenuse. So the cosine of the inverse sine of 2/3 actually equals square root of 5 over 3. That's an exact answer. Oh, one thing I forgot to mention though. You have to be careful when you first start here. You have to figure out which quadrant you're in. Where is the sine? First of all, it's an inverse trig function, so I know it's got to be here someplace. And where is the sine positive? In quadrant 1. That becomes important now, because when I go get the cosine, since I'm in quadrant 1, the cosine is positive. Let's do one more problem like this. How about the cosine of the inverse tangent of 3? Wow. This is not a special angle. I always tell myself the inverse tangent of 3 is actually be an angle. Another way to write that is, really what I'm saying is, the tangent of theta equals 3. Now let's figure out which quadrant theta is in. Inverse tangent, right, has to be between negative pi over 2 and pi over 2, either quadrants 4 or 1. Since the tangent's positive, once again, I'm in quadrant 1. So I keep that in mind as I solve this problem. The way I figure out what theta is, build a right triangle. Tangent of theta is TOA opposite over adjacent. And hypotenuse is going to be 3 squared plus 1 squared, square root of 10. So now I can say cosine of theta, so ca 1 over square root of 10. And since my angle's in the first quadrant, cosine's positive. And there we go. All right. It's a little interesting. Hopefully, as you work these problems and think about it, you'll get the hang of it.